Yeah, so hello everyone. This is our week 6 and we'll be. Wait, this is not going. Oh, okay, it went. Okay. So this week is all about diffusions and flow constants, flow rates. So it's all about how to represent a scalar as a gradient of a vector quantity that you know. Or if you have a differentiable quantity that's a scalar, then in front of it should also be a scalar quantity. So and the assignment also follows to the same. So it's more focused towards diffusion, gradients, flow currents, and those things. Okay. So to start with, we are already on week 6. We only have 2 weeks left, week 7 and 8. For that, we'll also have an extra session this week. It's probably on Sunday. You'll get an announcement for the same. So we are having this course, Introductory Mathematics, Mathematical Methods for Biologists. It's by Professor Ranjit. Then I'm his PMRF NPTL TA, Jagruti, from IIT Gandhinagar. I'm currently a fourth year biological engineering PhD fellow here. Okay. So to start with, of course, every time I add these things because you'll have some reference for the points that we have learned through and it just gets in and you never forget about those because these are like some preliminary concepts and phenomena that will always help you whenever like as in how you do or whichever type of studies you are trying in your entire journey. Okay. And then followed by it, we also have here. So these are like the differentiation formulas that we have seen. You know, now till this point, I expect that each one of you who are going through this video do know about this different rules and it's by heart to you because of the number of problems that you have solved till then. Okay, then you have for integrals, you have two different types of it. For integrals also, if you change the order of for definite integrals, the order through which you are trying to evaluate your integrals, then again your type of the nature how you'll do the integration that will also change there based on constants. It's also different. Now it's not as differentiation where you if you are like doing a differentiation of a constant, it will give you zero. In this case, look at the limits. So don't just adhere to what's inside because definite integrals are all about the bounds that you are evaluating them into. And then there are certain rules for it. So at this one particular stage, I'll try and suggest you that you go through the trigonometric formulas because till this stage you are well aware that how to solve these points, and these are like indefinite integrals. Those aren't evaluated within limits. Of course, for in this type of integrations, if it has to be, it would be in with respect to pi or radian. So either degrees or radian. And for this ones also, you can go and check something as change of variables for integration. So that will also give you an extra scope to learn into it, where you can change the variables to ease your simplicity so that how to solve it. Because you might wonder if something as x is written here, how come the term here is coming as that? So you can understand that concept from this one particular law. Last time we saw about exponentials, how exponential growth are about. Yes, let me just give you allow mic access if people join. Yeah, and then like the opposite for them is like we saw exponentially rising curves, and then there were the ones which were like decaying ones. So, and then we saw how a scalar and vector differentiate. So, one has a magnitude, other has a direction and magnitude both. So, there are like equal quantities that in like in naturally we just say that the speed of the vehicle or velocity of the vehicle, but essentially those two have two essential different meanings behind it and also an additional quantity next to it. Okay, so one is a vector, another is a scalar quantity. For example, your distance and displacement. Distance is something which you directly cover, whereas displacement is a shortest distance with respect to the direction it was being traveled through. Okay, so that's like a basic difference in between scalar and vector quantities. And essentially, all quantities will have such hidden differences. You just need to notice where this additional direction term is being quanted into. Okay. Then we looked at different quantities. After that, we went into vectors. We studied how vectors are. And this was like one such concept for vectors that how do you define a unit vector? If you divide the vector by its own magnitude, it becomes a unit vector. And there is a difference how you represent a vector by. It's like you have an arrow on top of it, either you have a hat on top of it. If that's a hat, you define it as a unit vector. Okay. Then we looked into polar coordinate system. So here we only focused on one such case where you have everything as spherical, because in nature we do see that the cells and the systems that we are working into, this in vitro systems, those are all from spherical mammalian cells or bacterial cells too. But in some cases, as retinal cells or some, will have a staggered morphology. The morphology would be different, something as that of a neuronic morphology. But in this case, for simplicity assumption, we are only looking for spherical coordinates. So if you have a region, if you do have something as a sphere, which, and then if you know the distance, the minimum distance from the center to its periphery, which is being called as radius here. Now, by how much distance or arc are you changing this radial distance can be defined with respect to this theta, and later you can define those with respect to your other coordinate system. So one can be as cos component, other can be sine component. Now, however and howsoever you change this theta, you do have the information about your arc of the radius as well as the structure, or howsoever you're looking at the entire spherical being here. Okay. Now, followed by it, we'll have some gradients. Last time we looked into gradients of concentration, and that was all. Where we looked, where first thing that we looked was about, what was it? It was about concentration gradient, right? Where we did had this diffusion constant, and then we looked at why it was negative, because it was in the opposite direction, so from higher to lower side. Now here also we'll look at the same thing. It's just that little bit introduction, and this week is like to some lectures I felt it was redundancy in between them, but probably they were included because of the example that the professor wanted you to see over there, so that you just grasp on it. Like you might have seen that the last two sessions are more of that one is only for 2D, one is only for 3D, and essentially nothing's changing there. Then in one such case, you have a relationship in between Einstein and this diffusion constants, and from where it comes. You might think that why a relationship that was like derived back in 1905, how is it useful now? But everything which governs this diffusion, flow rates, and constant currents do follow the same relationship till now in state. So people haven't moved forward from that equation, and that's just the one definite fundamental equation which defines your flow rates, their currents, and as well as concentration gradients. Okay, we'll also look at one important concept today also, which I mentioned last time, but we didn't go into it. Something about gradients, curl, divergence. So, and like I told you guys to refer into dot product and cross product. It you might have done, it's better. Not, we'll go through it. And it's just a small concept there so that you'll get useful to the identities which follow next to it. So that's why these all things are also, it will come naturally then. Okay, so till now you are aware that what a gradient is. That's nothing but difference in the concentration charge or something which is like changing in between high. It's like the value is being varied from high point to a lower point. Okay, so in between 2 points you're defining it, and then you do have gradients of scalar quantities. So you have matter and energy here which are related to some flow down gradients or concentration. It's also similar. For example, you take blood. So blood in case of from heart, now when it's being released through aorta to our systemic circulation, it's being released from an area where it is was at higher pressure, and then to our regions of body where it's at lower pressures. That's why they somehow say, sometimes say that don't be lied on top of your head, like most of the time when it's down there, because most of the blood will go into your brain, and it won't be good for you. You'll feel too much heavy that time. So that's why it's just something that how gradients fall into our feet should also get equal amount of blood, also our body parts also. So it's being told or advised that always keep moving, always have like once in 20 minutes, keep up, stand up, look here and there. Those things are there just because you have your good peripheral and systemic circulation. Okay. Now, yeah. So that was all about gradients here. So, okay, how this person is also moving, how he's carrying up the cart up. So now with here you see everything is related to the direction that it's following through, but now that direction is associated with a scalar quantity. So essentially what we are deriving here or looking at are nothing but vectors, which are nothing but velocity, flow, wherever they are happening into, in which direction they are occurring in. Okay. So whenever you take concentration gradient, how do you, so you already know till this point that what concentration gradient would be. If I define a curve as this, and at 2 points, I know if it's CA and CB, the points respect to it, you can also find it through the curve, like directly mapping it, linear mapping here. You have XA, XB here, you have CB, CA here. If you want to differentiate in between both of them, would be directly a dC by dx. Assuming that this delta x is very small, you can write this equation, or else it would be a partial derivative, or else you can write it in this manner. So from higher to lower, it would be CA minus CB by XA minus XB, right? So that's a basic definition for it. In case if you don't know how to write in the similar fashion, there are also ways where you can write for that delta X change, how much variation was there. So this is the delta X change that you have got to into. So in this case, it can always be from a higher concentration. It is always from a higher concentration gradient to a lower concentration gradient until it reaches equilibrium. Okay, so always whenever you look at here also, so if you have, so one such example was a concentration and the diffusion through which you have, so that's something about flow that you understand there. Next one is can be a force. Now for force, if you take an example of dam, okay, so whatever water is there in will have some sufficient potential energy. Now when the rotor moves, it will convert that potential energy into kinetic energy, and later how electricity is being generated there. Okay, so now you have conversion between one form of energy to another form of energy, and that gradient of energy is being converted into another form of energy. That's electricity that you're looking into. So force is nothing but also a gradient of the potential energy that you have. So that's like that's at most a good example that I thought that would be better for you to understand. So it's also a gradient of potential energy. So you can also write force as a gradient of energy. In this case, why it's again negative sign, it's also because of the direction which is following next to it. Okay, so always you see this constant. So we have looked into last time that how you write gradients as this. Now this is gradient of concentration. Okay, now this is a vector quantity, hence I've associated with it. Now how, if you have unit vectors associated to them, you write it as like this, and this symbol is nothing but it is called as nabla. Okay, this symbol is called as nabla, or you can also represent it as grad. Either you write as grad C or you write as nabla C, or if you only have vector, you write it as this one. Okay, so there are different conventions to it. Each and every time you write it, like given attention or notice to how you are writing it with. Are you writing with vectors, unit vectors, or only the quantity that you are trying to differentiate it against? Okay, so in this case, so this is like pretty much like you know this thing that gradient for a quantity is nothing but you derive the quantity in terms of all directions associated with the unit vector. So if you have a quantity like this, that's essentially equals to a grad f of xyz. So nabla times a scalar function is a gradient of the function and it is a vector, right? So we all know from this thing that it's nothing but a vector that's represented into. Okay, so now you know about force, you know about gradient. So we'll just write those equations here again. So force is nothing but it's a negative gradient of energy, because energy is a scalar quantity here. Also defining our diffusion for our flow cases. So it's nothing but negative gradient of our constant times the diffusion constant that we have for proportionality. Okay. Now for this forces, if it's like, again, if you consider into one particular direction, can be like a gradient of energy into that particular coordinate axis, like that be, let's say, ith axis times the ith derivative that you have. So n number, if you are looking into xyz, it can be xyz. With respect to time, it can also be with respect to time, an additional term can also be inserted into there. Okay, then you also have something as example of spring that was given in class. I don't know if I've added it, no. But how spring follows through, I'll just simply draw it here so that we are on the same track. Right, let's say at this particular point my spring had some energy of ex, then I tried moving it along this one particular direction as e2x. So now you know the energy or the force that I tried moving it or stretching up it into another direction was like definitely higher than the direction it was initially into. So this by nature follows that this E2x is higher than E1x, and how the gradient that we'll be looking at, and spring is nothing but an elastic quantity, right? So towards the end, it will tend to go into its original initial direction again. So our initial, the gradient that we're looking at would be in the opposite direction here. So how you write it as this with respect to the two positions that it's moving into can be E2 minus E1, can be the positions associated with it. Now, since our gradient is into the other direction, the force that it's coming back through, we can write this force as nothing but a negative gradient of energy in the position that you're looking at. Okay, so this one, either examples you take, you'll always end up with a similar relationship over there. Okay, so here we looked into potential energy. We looked into the differences of them. Similar case follows for electrostatic energy. We looked into elasticity. Okay, so these are like the different forms of energies what we looked at here. Okay, next comes is nothing but again one such example that I just wanted to include was electric field. So like we were only talking about flow, but now if you relate your volumetric flow rates to your Ohm's law, what you have, so V is equals to IR with respect to your volumetric flow rates. Always your flow is proportional to your current, the resistance and the other term is proportional to the potential difference through in between both of them. So if you just have heard about them, so here it's nothing but electric field in between 2 points, it's proportional to the potential difference in between the two. When it goes from one direction to another, it's like negatively has a index of it because of the quantity which is being reduced in one direction. So here you can also write as electricity or electric field, sorry, not electricity, electric field has a negative gradient of potential. Similar terms, but it follows way through. So it's like this. So this is like one such for electric field. This is not energy. Okay. So this was one example that I wanted to include. Okay, after that you have something else. But now, so till this state, you know about diffusions, you know about concentration gradient. Uh, yeah, that's all. So we'll just directly come up with dimensions formula there because you have one such question there in assignment. How what's the dimension for the quantity? So if you have a flow for so diffusion, how you represent it as negative gradient of concentration times your diffusion, right? So how do you represent, so what would be a unit for this particular quantity that you're looking at? Okay, so how you represent this one is nothing but concentration difference or concentration gradient across a point, right? So now this is nothing but something as how many number of particles would be moving across the area per unit time, right? So how much particles are moving through that concentration gradient across an area with respect to time. So number is like unitless, and then you have area as length square, and you have time as something, let's say this quantity. So when you're writing dimensions, always add square brackets to it because those are like so dimensions across. Now here, don't confuse this time with temperature. It is time. Okay, so this can be 1 by meter square second. So it's essentially nothing but meter minus 2, second minus 1. So this is like a unit for the flow through a particular gradient of concentration difference having a diffusion constant of d here in this case. Okay. So now if you directly also see this one, now what's your concentration difference? Concentration difference. Now in this case, let's just assume that this not assume, but the concentration that we're talking about is nothing but across a volume of volume cross section. Okay, so this would be nothing but number of particles in a volume, and this sorry, particles in a volume, and what is concentration, which is nothing but dc by dx, this gradient that you're looking it up. And then you have again x, so x is nothing but length, right? So what is your volume? Volume is again L cube. So this total will give you something as 1 by L power 4. Right. Now, if you have this as L power 1 by L power 4, the term in front of you, you have like 1 meter square second is equals to 1 by L power 4 times your diffusion constant. So now you have your diffusion constant as meter square per second. Okay. Or you can also write it as meter, sorry. It would be meter power 2 second power minus 1 and this one. Okay. So that is your dimension for this diffusion constant. I am very bad at memorizing these units. For certain units which are like, okay, day to day, we are just going through them back and forth. We can, like, we do have an idea about them. But for other cases, if you don't have, always keep in mind that you can represent them as with respect to measurements and units, what you have learned. So can be length, time, and the others, like just follow up into length and time. Those are like the basic fundamentals for it. Okay. After that, for one particular, so if you have a slide here on Brownian motion, this was one nice GIF here, but it's not playing now. Probably in the slides that I'll be posting into the drive link, you can have a look there. So what is Brownian motion? Just getting a sudden jump from gradients and concentrations into this Brownian motion. How is it related? We'll just see, but I just wanted to explain one phenomena about internal and external forces here, because what we just looked at was something because of this diffusive flow. This diffusive flow is only because of concentration gradients that we look here, right? Now this type of motion is very random. It's because of, like, it's very zigzag motion, and this is like in the absence of external forces. You do not have them. So this is nothing but because of continuous oscillation of the molecules from one part to another part, and they move very fastly and freely if it's a less viscous medium. Right, let's just denote it like this: in a very less viscous medium at higher temperatures, because they would be less dense in that point. So if you see over here, so this one such case where you have no external forces added into. Now, if you have external forces, if they give some part of attachment, attraction to your particles being moving from one to another, or if you're applying a force there, then that becomes a different kind of, then like that kind of flow is like a different flow there. Okay, so if we have to define that kind of flow, which are like if you give an external force, how you write it as the gradient can be the concentration times the velocity that it's moving through. And this is nothing but the velocity is coming through the force which is driving the velocity, right? Because of the force that you have applied, you have the velocity here. Now, in this case also, I'm just trying to have you into, so if you have this, and then if you have this length by time, you look here that, sorry, this was L cube because you had volume here, and then if you look here, this is again L square T. So here our unit are always conserved. Okay. So this is essentially the same in this case. So now if we just look for a viscous medium, it in terms of our bodily fluids, it can either be a fluid, it can either be blood, or let's say cytoplasm on those cases. In that case, you have something as drag force. Okay. Now, what this drag force are? These are like some resistive forces, and these are the forces which act in an opposite direction, which are moving through across a fluid. So, for a drag force to be defined, there's direct formula for it, and we are not deriving it here, but it's something as you write it as 6 times pi eta A and V. But here, the major assumption is that what the object that you're trying to look at is a sphere and has a radius A. Okay, so that's a sphere radius A, and this is viscosity. This is velocity, right? So that was an assumption there. Now, if you want to derive velocity here, it can be written as force by 6 pi eta a, right? Now you have this thing. Now notice something here that, okay, this force is also a vector here. Now something as that always our velocity is proportional to our force, and those aren't in the opposite direction. Those are like both are in similar direction because we do not see anything as sign here. So whenever you apply a force per unit that force, you always have velocity in the similar direction. So that's like well understood that, okay, if I'm pushing a person in one direction, he won't fall in the other direction. Because of the nature of force that I'm applying him, he'll always go towards the direction that I'm tempting him to. So it would be in the similar direction. So just to revise again, that when we look at diffusion, what's happening? Oh, it's making a line. Okay. When we are looking at diffusion, we are looking at concentration gradients. And then when we are looking at external forces, those are like force derived things. So then you're looking at the force and the local concentration gradient that is being changed there. So here everything is based on this force. So one such process here, this process can be called as passive facilitated processes, whereas this one is active process where you need something to initiate the reaction or initiate the action that you're trying to look at. Okay. So that was one part. So I guess I do have an example for it, but probably will take some time. So we'll see. Now we have the relationship in between this. Now, if you want to insert in between this formula, you have J as you just insert velocity there, concentration times F by 6 pi eta A. Okay. Now, I won't go over the same example, but I'll just tell you in short that if you assume a container, sorry, the container is not, but if you have some bigger particles in there, the bigger ones will tend to settle down, whereas the smaller ones would be on top of it. Okay. So at first, you'll have something, a force which is due to gravitation would be followed downside, and due to sedimentation, all the concentration would be coming up downward. So you'll have a concentration gradient below. Okay, because of the flow there. But after a point, because the concentration is different now, so they'll start to achieve a position of equilibrium there. So then you have a diffusive flow upwards in direction. Now you know one can be because of the concentration gradient, this one which was happening later. So this is defined as concentration times the diffusion constant, whereas the other one is nothing but because of the velocity because of which they are moving. Okay, so this JF, you can write this as C. Okay, don't forget this one's here, can be written as this, right? Whereas the other one is nothing but gradient. So that can be written as minus d and delta this. Okay. So this is fine. Now, when do you like achieve this both states? So when they would come at a point where it's at equilibrium is a relationship that Einstein discovered back in 1905. Okay. So how they did that was now governing that this concentration change is happening. After a point, it will start decreasing, right? So now we saw that, okay, it came up to a point where it achieved its higher concentration, lower concentration was separated. But now it wants to get into a position where there are equal amount of spheres. Let's say there are smaller and bigger spheres in one direction and the other one also. So now they tend to settle down. So that is followed by a exponential decay, which is similar to how your, I won't say the exponential decays that we looked into. So here it follows a relationship as this concentration decreases as a factor of fx by something as kbt. Okay. Now here, what is here in the exponential? What are the two things ratio of fx and kbt? What are those things? Any guesses?
Energy.
Yeah, yes. So we thought, sorry, not thought, but we saw when looking at exponentials and the constants which are there, two exponential in the power of exponentials are always unitless. So the quantity that you have on top, this fx, and quantity that you have in the denominator kbt, both are units of energies. Okay. So this is force times the displacement or the distance it took to. That's direct definition of energy. Whereas the other one that you're looking here is something probably some of you might have seen, or like you might have seen in your class, early classes of our, like our early science physics classes. So this is Boltzmann constant, the other is temperature. When you multiply both of them, and this comes into statistical mechanics. So it tells you about the rates of phenomena and processes that we are looking into, mostly into thermodynamics. So this is also unit of will also, one is nothing but joule inverse, and one is joule inverse times temperature. If sorry, it's not like that. It is joule per temperature, and then you have temperature. So essentially it's coming into joule. That's your energy that you're looking up there. Okay, so that was a point I wanted to emphasize there. Yeah, so now if you insert this C in here where you have this, because now you'll write it as minus d del C by del x, and then you have this x cap. You might have seen the entire derivation what professor is also doing. So if you do insert your concentration here as C is equals to E naught this, towards the end, I have written this, towards the end, I have written like formula that your JF, oh sorry, your JD is equals to DC, and then you have something as F by KBT times X cap. Okay, so I guess till now you can directly derive. So whenever you are doing this, we only have one chain rule over here, that this X. So you write this entire term as e raised to X, and then you differentiate this X again. So this all term will come outside, and this concentration is essentially because you have the whole term repeating itself. So you have C here, and then this is D. Okay. So if this is clear, then we have this term as force. Now, if you equate both of them, when both of them are same, that's nothing but we achieve a stable equilibrium direction in magnitude, but not in direction, because direction is opposite as we looked up here. So JD and JF are always opposite in direction. But when would their magnitudes be equivalent is a point that we have to look at here. So when you do this thing also, you get a diffusion constant as KBD by 6 pi eta A. Okay, so this is a relationship that you should know. If you don't even know, always derive it back, because there's no need to memorize this one particular formula. And it's not that at all times this would be decreasing. Okay, there are also special cases for this diffusion where you see that after a point when it's decreasing, because it's a natural phenomenon, it will tend to decrease, increase until it's reaching its own equilibrium state, and then it will also increase back. So you might also need to incorporate into factor where it is like essentially increasing as this. Okay. So there are like both ways to a coin. Similarly here also, it's increasing in one fashion, whereas it's also decreasing in the other one. Okay. So is this clear till diffusion constant? And I guess you might have also solved it when professor was doing it. If not, I highly recommend to solve this one particular derivation so that you get onto this diffusion constant formula. Also, to insert this exponential into, so this equation A into this equation 1, and then get it's like a direct equivalent of it and solve them both. Okay. So is this clear? Yes, you were saying, Shweta?
I was saying it's clear.
Oh, okay, okay. No doubts?
No.
Okay. Okay, so since we have done that, then we have this diffusion and concentration. It was directly given. Like, how do you see the change with respect to the spatial variations in the all three directions? Again, if you also consider with respect to time. So I guess till now you can directly write it as it is. And then it was that if it's not changing in one direction, it's like with respect to two positional points, then it's essentially equals to zero. Then the time derivative of it's also zero. Now, if it's not changing, if it is yeah, if the change is too small for it, it would be zero, the time derivative for the concentration gradient. Sorry, for the concentration gradient would be zero if it's not changing, and if your delta x is too small within the positions that you're trying to look at. But in cases where it is changing, the positions do have a change of, let's say, the small delta x, and your flow because of them do also change. So that's nothing but will follow a relationship of continuity there. Okay, so you'll essentially have your concentration gradient as a negative of your flow gradient. Okay, where you're looking into. So this is something how you write as continuity equation. There would be some initial bounds to it, but for now you can directly assume. So it's like it's just that you have this as negative del c by del x, and you can write this del c by del t as also negative d, or this negative will become positive now, and then you have the square of the partial derivative by del x square here. Okay, so that's just one thing. Now when we do that, all of the things that you are seeing here, just notice that each and every time we are writing this as this. Okay, and that's how it is actually telling us that if this is something as this, then if you have something, well, last time we did something as, okay, I told you that just multiply one direction, the magnitude of a particular position vector into the other position vector for a vector that you're trying to like you're multiplying it with. So this is nothing but essentially dot product. Okay, and also when you dot product for quantities or other vectors, sorry, if you add a dot product for vectors, their essential meaning is you multiply the magnitudes of them and then you add a cos theta for it. Here it's being accounted into when you're doing it linearly. Okay, and this is how you do it trigonometrically. So both ways if you do, you'll get on the same formulas. Again, this one is not being done here because you don't have the information about the degree of variation that here that you're looking at. Okay. Uh, then you know about this thing that we just did. Here it's dependent on initial conditions and boundary variations. Okay, both of them. So like there are some things that professor taught into. So that was about how if you take a Gaussian function, how the spread of the Gaussian function and how variations there are being defined into. Then towards the end it was more into as that how there are direct formulas for it. So I don't know if it's like if it should be motivated enough, but yeah, if you look for a Gaussian function, so these are like there are some certain derivations behind it. If you take the square of the average function, you derive it as 2 dt. So that's a diffusion constant, and with respect to time that you're looking into, this average you can also write it as x bar also, okay? So when and then if you take a square root of a one particular squared quantity, it's an absolute quantity, okay? So you always have two phases for an absolute quantity, positive and negative halves. So when you're looking into this kind of quantities, you always have something that is called as root mean square. Okay, so root mean square of that quantity would be square root of 2 dt. So here he said something as that always this is proportional to square root of t. Okay, but in cases, so this was when you are doing passively. So this was when you are doing diffuse flows. Okay, diffusive flows. Now, when we do have forces due to some external force that's being applied, so forces due to those external forces as something, let's say, our velocity. Now, that's being derived as distance by time. You can say it as x by t. And here we write as v is equals to xt. So here you see, because of this external force, this x is directly proportional to t. So what you wanted to tell from here was this is a part of some active transport. It wasn't clear how directly he came into this linear relationship, but it was this one. And for diffusive, he meant to say this because all we have an assumption here that they follow a spherical object, which essentially follow a Gaussian nature. And hence, when you're trying to look at its own velocity, the spread or the variance of that function, it is nothing but dependent on the square root variation of the time that there you are looking into. So those were like the two terms which had, and that's why I guess I probably included the Brownian motion. So it was more to tell you that in terms of diffusions, you have two processes. So this, like, we are going into a little bit of biology, but you have something as facilitated diffusion, and that's a passive process. Okay, and then you have some active diffusion, which is happening because of the external forces that you're applying into. So here it's all about that, what we are looking into. Just because it's passive, we have taken an assumption that it will follow this one distribution. And from that distribution, we are trying to follow that, okay, how would our one variable, position variable, would vary with respect to the time variable if the diffusion constant is known to us. But in other cases where you directly have a force known to you, in those cases, it's directly proportional to the time variation of the forces that you're looking into. Now, this time variations can essentially be your spatial variations too. So those are like directly equivalent in both axes. Okay. Apart from that, here, yeah. So this was one thing that I wanted to highlight also. So last thing, that this dot product is nothing but if you take gradient of both of them. If you take gradient, oh sorry, dot product of a gradient and a velocity vector. Here in this case, just assume that it's velocity because you have like been known to it for a while now. But it can be any vector. Okay, so that's a scalar quantity that you're looking into. So this is defined as divergence of V. How you call it officially is a divergence of V, not always as grad C or grad D, because it's just gradient. That gradient is only, it's like it's only with respect to the del parameters. It is not with a vector that you're defining it with. Now, when a vector comes into play, that is a divergence of a vector that you're looking at. But if you do cross product in between a gradient and the vector that you're looking into, would be a curl of V. Okay, and that quantity tells you a vector. Till now, we were focusing into force, energy, concentration, diffusive flows. Those things all are for a scalar. Hence, we are only looking into grad products. So those are only divergence. Okay, that's one terminology here. Whereas later, when we try, I don't know if later it's being included in here or not, if you do have a concept of certain things in biological states or systems or not, but something like that exists in mathematics. So if you do take a cross product, you have something like this. Now, what a cross product is, it will follow a matrix there. will just give you certain hints into it so that if you are interested into can look into it. Let's say if you add x cap, y cap, and let's say z cap, and you have certain numbers here, a, b, c, d, e, f. Okay, let's say we have a 2 by 2 matrix in this case, or two vectors to solve this many phenomena. Okay, so in this case, how do you do is that you, if you're trying to write it for x cap, okay, it's like hide this column for x cap. Okay, just hide it back, and then you take a cross product. So just multiply these two terms minus these two terms. When you're doing for y, just hide this term. You do for this one and this one, multiply both of them minus the other ones. When you're doing for this one, hide this one, write z cap, and then this ae time minus bd, like that. So that's how you're writing a curl quantity. Okay, so here also if you look here, for the ith one you're getting components from z and y. For the jth one you're getting components from x and c. For kth one it's components from this and this. You never have bigger matrices to solve for this particular curl divergence product. So always this small matrices work there. So it's not of an hassle to directly solve it. It's very easy. Just if you'll need calculator in times your calculation gets heavy. Okay. So that was one concept that I wanted to highlight here. One is divergence, another one is curl. Okay. So this, oh, it got height in there. So that was something I wrote there, that diffusion versus flows. But okay, this is a phenomena that we just talk about. For active transport, you'll have the molecules do its own thing. And you're getting the energy from certain other binding molecules which are there inside. Would be an ATP to drive your membrane through it. So that would be the diffusion, and that's the driving force that's causing the diffusion to follow through. Whereas in terms of passive, there are two transports. One is like diffusion through concentration gradients, and one is like facilitated. You have certain membrane proteins which will help you move from one concentration gradient to another concentration gradient. Okay, so those are like two direct related phenomena there. Okay, so that's it. Do you have any questions, or else we can jump on to assignment then? Any questions?
No.
I guess someone said no. So I believe we can go into assignment then. Week 6 assignment. Yeah. You also have 10 questions here. Here you go, the first one. That some proteins diffuse along DNA. The typical coefficient there is 10 raised to minus 12 centimeter square per second. So here you see it is, it's not letting me write. So it is something as length square per second, right? What is that unit for now? First thing. And then you have what's the value of a frictional drag coefficient for that protein. So we just looked into a drag coefficient, we just looked into drag force for it. Now what would be the drag coefficient for it? So I can give you a direct formula for it. If this pointer is selected. So you, in this case, it is nothing but kT by your diffusion constant. Now you know which quantity is what, right? So you have been given, oh, you are not being given. So assume that this thing right here, not assume, but it is. But I don't know if for what we are talking about. We are talking about a protein, but let's say if we are giving certain temperature and certain variations there which exist there in body. Why it's not letting me write? So this is like 4.2 times 10 raised to minus 21 joules. And then you have this quantity with respect to your diffusion constant. Then you also have Kelvin there. So it would be something as 10 raised to minus 12 in this case. Hmm. And then you have 10 raised to minus, I don't know from where is this 10 raised to minus 4 other is coming into. And finally, you have this in meter square. Oh, wait a second. What is the unit for this? This is centimeter square per second, right? So we need to convert into meter because everything we are talking in here is our SI units, right? So then this would be 10 raised to minus 4. When we do that, we are converting this into meter per second and we are no longer into this term. So we can compare both of the terms here. The final unit that you get is something as grams per second. Why grams per second? Because you have energy right here. And for energy, you can do your calculations as force times distance and this Newton meter. Force is mass by, sorry, force is mass times acceleration. So you have meter square second. This slash is not here. K, oi. You have something as kg this, and then you also have a meter, and then you have gram per second. So what would you answer here? Yeah, so if you just look into this ones, this essentially makes up to like 16. And then when the 16 goes up, it will give you as 5. Oh, does not add up to your this thing. Oh, so this 5 would be minus 5. And then you just do as 4.2 times minus 5, what it would be. Not minus 5 though. But yeah, so okay, so when you're doing minus 5, you want the answer in grams per second. So you look at the units now. We were essentially into kgs, so then you have to multiply it by 3. So then you have 10 raised to minus 2 and 4.2 times 10 raised to minus 2. So what would we answer then here in this case comes up to with this. Okay, this is all about units. When we're looking at diffusive flows, when you're looking at concentrations, all about units. If your units fall into, you're good to go. You don't even need to know the theory behind it. Okay. Now
I
here.
just had
Uh,
one doubt in the previous
yeah.
question. How did we get that formula C is equal to KT by D?
So that is directly from, sorry, this formula is not given here, but this follows this frictional drag coefficient. That's why I wrote it directly.
Okay, okay.
Huh. So the one that we looked into previously as what it was for velocity, how it was that F by 6 pi eta A. From this, you have a KB constant. And from that KB constant, this comes. That's why I directly wrote in here. So you don't need to learn these formulas. This is just for assignment. That's why probably they haven't given it here. But if it's for your exam, such formulas which are not part of the curriculum, because here you don't have to memorize formulas like this, which were there in some basic preliminary physics or let's say in some advanced physics. I don't know from where it comes. But what you need to know here is how concentration and flows are being varied. So that's the only thing that you should know here. Okay. Next. Imagine a particle diffusing in 1D. Okay, so that's just 1D that we're talking into. Okay, so you have a root mean square distance of the particle in 1 hour is 4 centimeters. So you have root mean square distance of a particle in time t equals to 1 hour as 4 centimeter. Calculate the diffusion coefficient of the particles. So I told you that this week probably would be more of this. So now we went and looked into this equation, right? We had this 2dt. Now what they are asking us, so this is root mean square. So this is x RMS as square root of 2dt. But he's telling us to calculate the diffusion coefficient, which is like this d. So for that you need this x square divided by 2t is equals to your d. Okay. So then you do the calculations here. What would the answer here?
Be 8 centimeters square. Sorry.
Exactly. This would be this one. But yeah, I do doubt that if for all spherical beings you can directly different like assume it to be Gaussian in those cases. Of course, I know that if you do microscopy, all objective functions do have a Gaussian distribution following through it. But if you are trying to like generalize for cells, that's not how it should be done. Probably it will get more complex how it's differentiated, and since it's just basics for now, they are telling us just to follow Gaussian, but if it's like a vice versa question given in your exam, that if all follow this, but Gaussians do model this one, then it would be definitely a false question. Okay. Okay, so then we have a numerical based question here, that a sphere filled with water like a cell. Okay, then we have a protein molecule placed at the center of the sphere. There are two ways in which this can reach the periphery of the cell. One is diffusion, then second is this active motion. I guess you do understand where this is going now. So assume that you have a radius of r, and then in case diffusive, calculate the time it takes. So for diffusive, it was directly proportional to t, and for the other cases, it was proportional to root t, right? For the protein to reach the periphery of the cell. So now the diffusive coefficient is given to us. Would someone like to try in here? I guess you can see the answer in this case. That's 8.33 if you want to try. So can just start writing how it's like this x square follows as your 2dt, right? And then we just want to calculate the time in this case. For the periphery, in case 1. So for the diffusive case, that's why we are doing this one. And this is like x squared by 2d. I guess that's it. 2 times 2, that would be your 4. And on top of it, you have this 10 squared, so that's 100. 100 by 4 is 25. But now units. Where are we lagging behind? We have micrometer, micrometer square per second. We have temperature values there. Okay. Now, whoa, where are we going wrong? Like, if it was not about for this question and I didn't have the solution key, I won't have realized. But it's good that we are doing it beforehand. So we did notice that if it was a radius, but now here this x stands for the entire distance that it's traveling through. Okay, so it's basically your sorry, yeah, if I'm writing it correctly, not this x here. I Oh, we didn't have to change the radius. Diffusion coefficient. That's concentration square by this. Then will it be the one that how just we calculated as like 100 by 4? Will it be just 25 then? But this is 8.333. Previously, I was thinking that it would be this one. Oh, yes, sorry. Really sorry. So how's your relationship between diameter and radius? Radius is diameter by 2, right? And then, yeah, this is the entire distance that we have to follow through across a sphere. So this is like the dia that we are talking about, but what's being given to us is the radius here. Okay. I was very confused that why is it like that? And then here we have to calculate. So this would be d squared by 4. So you'll have 100 by 4. So that's sitting over 25. Now we want to do something as where it went. Here 25 by 2. So this is certainly wrong then. It's not this one. Oh. Now here we are looking at a sphere. So the radius there won't be directly as concerned how our circular ones are. Okay. And in that case, you have something as 4 pi by 3 r cube relationship with respect to volume. Let's just Google online how the radius and diameter of a sphere are related. Diameter, radius of sphere. Do anyone of you know about that? It's similar. It's always half of its diameter. But how these guys have written in the solution it is that they are doing as this 25 divide by 3. And that's why I thought I will have this 4 by 3 something, the constant out there, which gives out to be this one. But the other case would be that answer key is wrong. But it shouldn't be that easily. Let's just try and solve it. Hmm. Any guesses here? It just I'll look into the official key that I have from NPTEL. Till then, if you're able to crack it through, do let me know also. Hmm. I didn't expect questions over here to be this tricky. Let's just remove all of this part here. Try and solve it again. Either cases, the answer can be wrong. We can directly consider it. Oh, okay. So, guys, this is not me, but I just found it on an online source. Probably that's correct or something. But so how we looked up into a circular thing following Gaussian, we saw that is this x square was proportional to 2dt. Okay. But when it's for a sphere, for this mean displacement for a sphere is associated as 6dt. So that was not at all about the radius or diameter there. We always have the radius to be traveled through. So you'll have like 100 by 6 times 2. So you have like 20, I'm sorry. Yeah. So you have something as 100 by 12, which gives you as 8.33. So if questions like this come, you can always look at what they are trying to ask us here. I will try and see if from next time they do give a hint of the relationship what it is following through, or else how will we know that which relationship here we are talking about, because we didn't even derive it. Okay, so this was something else. Yeah, but still till now I'm not yet sure if this equation is following. I just saw it on two sources online. I don't know if that source, how accurate that source is. I just looked up into
The
one YouTube video. Hi, yes.
the professor had told, I think, for 1D it's 2dt, for two-dimensional it'll be 4dt, and for three-dimensional it'll be 6dt.
Oh, that's great then. Okay,
So
there you go then. Okay. Okay, then you have this one. Then that's true, probably. So this is something for a 3D, and that you get from here that this is a sphere, which is a 3D. Okay. Okay. Then the next question. In this case, for active transport, calculate the time it takes for a protein to reach this one. So can you do this then? So for this one, for the fourth question, since it's an active transport, I do hope that what I remember is correct. So it would be directly dependent on it. And then we have x given with us, that was 10. And then you have a velocity, that's 2, that is time. So hence you have the answer as 5. Okay. And its unit would be a second, because this is micrometer per second and this was micrometer. So you have a second. Okay. Uh, where did my screen go? Yeah. Okay, next question. Consider the above two questions, Q3 and Q4. If we increase the radius 2 times from this to this, the time to diffuse and the time for active transport would be what? So in one case, you had something as 6 dt. The other case, you have like dt. And you were trying to change the radius. So here it's like square root of it, because it's, no, x square, it's proportional to 2 dt. In the other case, x is proportional to vt. Now we have to calculate how the radius is being changed. Time, oh, sorry. The time is being varied. So time in one case is a square root and other case is directly proportional to it. Okay. The square root of x, I guess x is square root of t, so t is x square. Uh-huh. This is x square and the other case is directly proportional to it. So it is nothing but if one is twice, the other would be half of it. So let's just see the formulas for it. Yeah, so there you go. That's one. So if the other one is, we need the ratio in between this a to b, something like this. So we want the upper one to be higher one. So that's the answer. Yeah. Okay. And we have big numbers here. Some proteins do diffuse along DNA. Typical DNA coefficient measured along DNA is this. Okay, so that's our diffusion coefficient. Assume that the protein has a radius of 2 nanometer, and then what's the effective viscosity filled by the protein? So in this case, we had this equation as concentration is defined as 6 pi eta r. And then from concentration, as diffusion as kBt by C. So this equation, what I wrote previously. Okay, and concentration is like that. 6 pi eta r, or it can be either as 6 pi eta a. So now you have to calculate viscosity there. Okay, so you need to insert this kBt. They're saying simple rule of 1D diffusion. So what formulas we know till now, it's fine. Now if we directly insert this 6 pi eta r, and then we want, what do you want? We want viscosity. So this would be kBt by d, and then you have 6 pi r. R is your radius. Okay. In this case, your Boltzmann constant is similar how it was previously and times t also. So this the numerator is 4.2 and then it's 10 raised to minus 21. The other ones you can feed in, right? You have this 10 raised to minus 12. You have 6 pi and then you have a R of 2 nanometer. So now you need to pay attention to SI unit because here you do see the units are SI unit, SI unit. So everything would be meters. Okay. So need to convert this into meters, need to convert this into meter. And that's it because this is energy as joule. So it would be in SI units of meter, kilograms, sorry, mkg, yeah, meter, kilograms, and seconds. So everything should have been like that. So you have seconds here, convert this into meter square, convert this. So nanometer is like 10 raised to minus 9 meters. And then this would be like 10 raised to minus 12 times 10 raised to minus 4 meters square per second. Now insert everything in here. That's it, right? We don't need anything else. And pi you can take as 3.14, right? Pi can be 3.14 or 22 by 7. Adding all that, what is the answer do you get? Insert into calculators. I do feel this is like too much on formulas. Directly inserting values and formulas there. Any guesses? What would be the answer? So this is this one, and then you have a big quantity here, minus 16. And then you have something as 6 pi, and then you have like again a big quantity minus 9. This becomes minus 25. This goes up, so you have like 10 raised to power 4. And then you have as 4.2 by 2, and then you have 6 pi here. So 4.2 by 2 is 2.1, and everything you'll be multiplying with 10 raised to 4. So only options are like either this one or this one. So either cases you do the multiplication there, you'll get the answer. In this case, they're saying the answer is this one. You can check, multiply and see. Okay. This is something like a little bit less on calculations. So imagine a 1D tube through which a protein is diffusing. At a given time, the protein concentration is given as this. Oh wow, they're just asking us to calculate the flow here, the current here. So that is nothing but Negative diffusion of the gradient of the concentration that you'll be looking at. Okay, who can do this? We don't even have to insert formula values for diffusion constant here. Just simple. You can look it up. You directly have the answer in front of you, I guess. But look at the signs carefully. There is also a trick in here. A little bit too, not hideous trick, open trick.
Then we use
That's this one. Okay. I like questions like that. What's the unit of diffusion constant in SI units? So till now you all know. What's the diffusion?
C
Yeah,
meter
meter
square.
square. Yes. This one. And then the most influencing factor of diffusivity is what? So we just saw that everywhere, just try and remember wherever your diffusion was, what other parameter was there with respect to it. Okay. With energy also when you wrote diffusion, with concentration when you wrote diffusion, with Boltzmann constant when you wrote diffusion, what was the other factor which was governing there? What will affect diffusion? Exactly. So temperature. So that's temperature there. And last one. For flow, J. So that's a gradient of concentration by X. So no, sorry, it's a gradient of concentration, but concentration itself is with respect to other units, and then you have a length again. So what would an answer?
the second option.
Yes, that's a good option. Nicely done. The 3D question I just got me, but the other ones we were able to solve. If you have any questions, you can stay back, or else thanks for joining today. Any questions?
No, it's clear.
Thank you.
Thank you.
Okay, so then I'll be ending the session. Thank you for joining.